Good afternoon, everyone. I am Eda Montano, and today we will be talking about transformations, specifically tilings revisited and dilations. Okay, let's get started. Now, we will focus first in tilings revisited, and this time we will define a tiling first. When we talk about tiling, a tiling or tessellation of a flat surface is the covering of a plane using one or more geometric shapes. To illustrate further the idea of reflections, rotations, translations, and glide reflections, we want to begin the geometric analysis of wallpaper designs. A wallpaper design is a tiling of the plane that admits translational symmetry in two directions. That is, the design can be moved into different directions and coincide with itself. So we can really see here the application of transformation, most especially in wallpaper designs. And later on, I'll be showing you the different types of wallpaper designs. And there will be 17 types, and we will be able to show that later. Okay, now let's move on to the next slide. Now, for example, in this particular slide, I'll be presenting to you a simple shape, and then we will try to replicate the following shape so that we can eventually tile our plane. Okay, this is square, and then if we will make a rotation, let's say for example a 180-degree rotation, then we can have another figure. Okay, and then if we will also apply the options in transformation, let's say you will have translation or even reflection, then you can really tile the entire plane. Okay, so let's have this one. Okay, okay, now that will result to a checkerboard. Okay, now to illustrate a further detail of this one, we will mark the following. Okay, mark in the red, mark in red are the center of rotation. Okay, mark also in blue are the center of rotation using 180 degrees. In the red part, that's 90 degrees. And we will also be seeing the bold lines. And these are the mirror lines. Okay? Now, let's have this. This styling is classified as P4M. The smallest rotations allowed are quarter turns, and there are reflections in four directions. Successive use of reflections and rotations fixing the design would replicate the whole tiling from just one white square and one colored tile. This time, we will have the short table of characteristics of the symmetry groups. As you can see, we have 17 groups. And then we also have their notation. We have P1, P2, PM, PG, and so on. We have the lattice type, okay? Rotation orders, and the reflection axis. Okay? Now, let's see the different types. Let's just go over with the following types of wallpaper design. Okay, let me just use the laser point. Okay. Now, let's just observe the differences. Okay, all in all, they are very beautiful. It's just that they have different orientation, of course, and rotation of figures. And then, if there's a common thing, we can observe a repetition of a certain object. Okay? Now, let's see the other design. Okay. And finally, this part. Okay? So, before we will end in the tiling part, I'll be showing you, after this one, how to tile a plane using GeoGebra. Okay? This time, we will make use of GeoGebra in showing you how to tile a plane by using the transformation tools in the basic tools shown above. Okay? So it is said that we can create a tessellation using the given application. Now, the first thing we need to do is to create any polygon. So this time, I'll be clicking this tool and then I'll choose the regular polygon. Then let's just create a pentagon. I'll be using a pentagon this time. Okay, now let's just move the object by clicking the move button. Okay, and then for me to be able to do the rotation, I'll just create midpoint of the segments. We have 5 segments here. Okay, let's just create the midpoint. Okay, now once we're done doing that one, let's just go to the transformation options and then let's choose rotate around a point. The first thing we need to do is to click the given figure and then we will be starting here in point F. Let's click point F and then I am going to use 180 degrees and the direction is clockwise. So let's use 180 degrees all throughout. Okay, do the same thing, 180 degrees. Okay, we will repeat this process. Wait for a minute. Okay, here we go. And this will be the last one. 180 degrees, clockwise direction. And finally, we have now our figure. Okay? Now, the next thing we will do now is to duplicate our figure. So, we will tile our plane using this one. How are we going to do that? We will use a vector. Okay? Okay, this is our vector. And then let's go back to the transformation options and then translate by a vector. Okay, select the whole figure and then click the vector and then you will be able to see another figure. Okay, so to duplicate the two figure once more, this time I am not going to use a vector but I am going to use a line instead. Okay, let's use a line. Let's just see this one and this one also. Let's use this part. Okay. Now, once we have a line, let's go back to the transformation options and then let's click the reflect about a line transformation, highlight the figure and then click the line. Okay, now you will be able to see the reflection. So, parang dumami yung ano natin. So, we will just hide the given figure. Okay. The same thing here. At the end of by the end of this one, you can actually hide all the labels, but we will not show that to save time also. Okay. Now, this time, you can just do the same thing and then you will be able to see exact figures. Okay. Let's have the next part of our topic. Let's talk about dilations. Okay. In this section, we would like to look into another type of mapping, which is dilation, that is frequently used in geometry. Dilation will not be an isometry, but it will have another useful property, namely that it preserves angle measure. Now, let's have the 4.5.1 definition. A geometric transformation is said to be conformal when it preserves angle measure. That is A prime, B prime, and C prime are the images of A, B, and C. Then, the measurement of angle A prime, B prime, C prime is just equal to the measurement of angle A, B, C. Okay, now just a little bit of clarification when we talk about conformal. A transformation again is said to be conformal when when you are dilating an object and then the angle stay the same. Okay, only the shape changes and not the angle measure. Now let's have the next slide. Now, dilation changes the size of the shape without changing the shape itself. When dilating, you are either enlarging or reducing the size of an object. For example, when you enlarge a photograph or use a copy machine to reduce a map, you are making dilations. The scale factor, denoted as K, tells you how much something is enlarged or reduced. Now, let's have this example. Now, this is our original object. Notice each time the shape transforms, the shape stays the same and only the size changes. Okay, let's enlarge the figure by 200%. Okay. And how about if we will reduce the original object into 50%? Just like that. Okay? We are just enlarging or shrinking the object. Okay, reducing rather. Okay, another example would be this one. Look at the pictures below. This is a star. Let's dilate the first image. Let me just use a presenter, a laser point rather. Okay, now let's dilate this given image with a scale factor of 75%. Okay, this is our result. Now, how about the second one? Dilate the image with a scale factor of 150%. Okay, now that would be the result. So see, only the size changes and not the particular angle inside the shape. Now, let's have the second definition. A dilation with center O and dilation constant K is equal to 0 is transformation that leaves O fixed and maps any other point P to the other point P prime on ray OP such that OP prime is equal to K times OP. Okay. Now, we will use GeoGebra to illustrate the given definition. Let's draw a triangle first. Let's click the polygon tool. Okay, let's just draw a small triangle. Okay. We will just rename the triangle ABC later on so that we will be able to satisfy the given definition earlier. Let's just make a point. And this will be our center point. So let's rename point D and let's make it point O. This will be the center of our dilation. Okay. Now, let's rename point A. Let's rename the vertices. Okay, this will be M. Okay. I'm sorry for that. Let's make this M. This will be P. And this will be N. Okay, here we go. Now this time, we will just click the transformation tool. And then let's dilate this object from this point. Let's click the object first and this one. Then let's just decide what specific scale factor to use. And this time we will be using 2 as our scale factor. It's up to you. Okay. Now, notice that we finally deleted this one. Of course, you can move that one. And okay, let's go back to its original position. Now, let me just draw a ray from this one to this one. And another one. Okay. And finally, let me just click the move button so that we can move this part. Okay, now let's go back to the definition 4.5.2. So, as I said earlier, point O here is the center of dilation, and the constant that we use or the scale factor is 2, and it's a transformation that leaves O fixed and maps any other point P on the point to the point P prime on the ray OP, okay? Such that OP prime is just equal to K times the product of OP, okay? And K is the scale factor. Let's have 4.5.4 theorem. The dilation transformation is conformal, and it was already presented earlier. Now let's have the last part of our discussion, 4.5.5 theorem. The image of a circle under dilation is another circle. Okay, we will make use of GeoGebra once more to illustrate the given. Let O be the center of dilation, Q be the center of the circle, and Q prime will be the center of the image circle. Okay, let's illustrate it now. Now, the first thing we will do is to create a circle with center through point. Okay, now let's rename this one. Earlier, it was mentioned to let Q be the center of the circle. Okay, and point P be a point on a circle. Okay, and then let's create a point, and this will be the center of dilation. Let's rename the point. This will be point O. Okay, notice that that would be our center of dilation. Okay, the next thing we will do is to, of course, dilate our circle. Okay, let's dilate from a point. Okay, I'm sorry for that. Let me just go back here. Let's click dilate from a point. Let's highlight this one. And then let's click this. And just like in the previous slide, we will make use of 2 as our scale factor. And this will be our result. Let me just drag this one. Okay, notice that we already have P prime and Q prime. Now, the next thing we will do is to go back to our proof. Let O be the center, blah, blah, blah. And then, by the theorem 4.5.3, P prime, Q prime over PQ is just equal to OQ prime over OQ. Now, we will prove this one by measuring the following. Okay, let's identify their measure first, and then let's see if they are really equal. Okay, we will refer it to the given formula. Excuse me, distance of P prime, point P prime to Q prime. That would be 3.58. And then let's learn about the distance of point P and point Q. Okay, 3.58 and 1.79. Let's go back to this one. Okay, we will get their ratio, P prime, Q prime, all over PQ. Okay, let's compute 3.58 all over 1.79. And the result is just the scale factor, and that is 2. Okay, now this theorem will be correct if we will compute the next thing. If it's wrong, then our illustration is wrong. Okay, let's hope it's correct. Now, let's have the distance of point O and point Q prime, and then point O and point Q. Okay, let's get the ratio. 6.9 over 3.45 must be 2. Okay? Okay, and it's still 2. Therefore, our illustration satisfies theorem 4.5.5. Okay, and that would be all. Thank you.